Welcome to DAR Tutors. Today, we will begin our exploration of chemical equilibrium, a fundamental concept in higher-level IB chemistry. This topic, R2.3, is titled How Far? The Extent of Chemical Change. It is essential for understanding how and why many chemical reactions proceed. The extent of a reaction, or how far it goes, is governed by thermodynamics, while the how fast, or the rate, is governed by kinetics. A key question we will answer is, how can the extent of a reversible reaction be influenced? By the end of this video, you will be able to describe the state of dynamic equilibrium, write and use the equilibrium law, and qualitatively predict the effects of changes on a system at equilibrium. Let's start by clarifying a crucial distinction: irreversible versus reversible reactions. An irreversible reaction, such as the combustion of methane with oxygen to form carbon dioxide and water, proceeds almost completely in one direction, from reactants to products. It's exceedingly difficult to reverse this process and convert the products back into the original reactants under normal conditions. Conversely, a reversible reaction is one where the products can also react together to reform the reactants. These reactions are represented by a double-headed arrow, indicating that they can proceed in both the forward and backward directions. Let's consider an example: the reaction between ammonia and hydrogen chloride. At room temperature, ammonia gas reacts with hydrogen chloride gas to form solid ammonium chloride, a white smoke. If you heat this solid ammonium chloride, it undergoes thermal dissociation, breaking down into its constituent gases, ammonia and hydrogen chloride. This demonstrates the reversibility. The same chemical components can be made to react in either direction by changing the temperature. This is a clear example of how external factors can influence the extent of a reaction. This brings us to the core concept of this video: chemical equilibrium. For any reversible reaction carried out in a closed system, a state of chemical equilibrium will eventually be reached. Let's use the reaction between hydrogen and iodine gases to form hydrogen iodide, H2, I2, and HI. It's carried out in a sealed container, meaning no matter can enter or leave, though heat can. At equilibrium, we do not find the reaction having gone to completion, but instead, we find a mixture containing all three components: hydrogen, iodine, and hydrogen iodide. Let's visualize this with a graph of concentration versus time. Initially, we have high concentrations of reactants, H2 and I2. The product, HI, has zero concentration. As the reaction begins, the reactants are consumed, so their concentrations decrease rapidly. At the same time, the product, HI, is being formed, so its concentration increases rapidly. Over time, the rate at which reactants are consumed slows down, and the rate at which product is formed also slows down. Eventually, at a certain time A, the concentrations of all species level off and become constant. The period after this time A, where concentrations are no longer changing, is when the system has reached a state of chemical equilibrium. So, what defines this equilibrium state? A common misconception is that all reactions have stopped. This is incorrect. Equilibrium is a dynamic state, not a static one. To illustrate this, think of an analogy. Imagine a person running up a downward-moving escalator. If the person runs up at the exact same speed that the escalator moves down, they will stay in the same place. They appear to be static, but they are in constant motion. This is exactly what dynamic equilibrium is. At the macroscopic level, there's no change in the concentrations or physical properties of the system. It appears static. However, at the microscopic level, both the forward and backward reactions are still occurring, but at the exact same rate. This means reactants are converting to products at the same speed as products are converting back to reactants, resulting in no net change. The system is in a state of balance. This dynamic nature is also confirmed by experiments using isotopes. For instance, if you establish the ammonia synthesis equilibrium and then add heavy hydrogen or deuterium, D2, to the mixture, over time, you would find deuterium incorporated not just into the hydrogen, but also into the ammonia, forming molecules like NH2D and NHD2. This is evidence that bonds are constantly breaking and reforming, even at equilibrium. This confirms that equilibrium is a dynamic, not static process. So, we've learned that a reversible reaction reaches equilibrium when the forward and backward reaction rates are equal, resulting in constant macroscopic properties. But what are the conditions necessary for this to happen? There are two main conditions for a chemical equilibrium to be achieved. First, the system must be closed. This means no matter can be exchanged between the system and its surroundings. Consider the decomposition of calcium carbonate. In an open container, the carbon dioxide gas produced would escape. This means the backward reaction, where CO2 reacts with CaO to form KaCO3, cannot happen. The reaction goes to completion in the forward direction. No equilibrium can be established. However, if we heat calcium carbonate in a closed system, the CO2 gas is trapped. This allows the backward reaction to occur. In this closed system, a dynamic equilibrium is established where KCO3, CaO, and CO2 all coexist in the container. The second condition is constant temperature. As we will see later, the rates of reactions and the position of equilibrium are all temperature dependent. For the system to be stable and achieve a true equilibrium, the temperature must be kept constant. While the qualitative description of equilibrium as a balance between rates is useful, chemistry students are expected to quantify it. At equilibrium, at a specific temperature, there's a fixed mathematical relationship between the concentrations of the species present. This is described by the equilibrium law. For a general reversible reaction, AA plus BB gives CC plus DD. The equilibrium constant, K, is defined as the concentration of products raised to their stoichiometric coefficients, divided by the concentration of reactants raised to theirs. Let's break down this expression. The capital K represents the equilibrium constant. Its value tells us about the position of equilibrium. Square brackets like A denote the molar concentration of a species at equilibrium, measured in moles per cubic decimeter. The exponents, A, B, C, and D, are the stoichiometric coefficients from the balanced chemical equation. A critical top tip for writing equilibrium expressions: pure solids and pure liquids are excluded. Their concentrations are considered constant and are absorbed into the equilibrium constant value itself. Finally, the value of K is constant for a particular reaction at a constant temperature. If the temperature changes, the value of K will also change. Let's apply this equilibrium law to a worked example. This example tests your ability to interpret experimental data and verify the constancy of K. The table shows equilibrium concentrations for 6 experiments of the ammonia synthesis, or Haber, process at 500 degrees Celsius. The task is to use this data to show that the reaction produces a constant value of K at this temperature. First, we must write the equilibrium expression for this reaction. The products are on top, reactants on the bottom, and the exponents are the stoichiometric coefficients. Now, we will substitute the equilibrium concentrations from each experiment into this expression. For experiment 1, we plug in the values for ammonia, nitrogen, and hydrogen, and calculate the result. This gives us a K value of 0.0602. Now we repeat this calculation for a second experiment. This is crucial for demonstrating that K is constant. Let's use experiment 2. The concentrations are different from experiment 1. After calculating, we find the K value is also 0.0602. The fact that we obtain the same value, despite different starting concentrations, proves that K is a constant for this reaction at 500 degrees Celsius. For a complete answer, you should perform this calculation for all experiments, as shown in your notes, to fully demonstrate the principle. Let's work through some practice problems to ensure you can confidently write equilibrium expressions. For each of the following reactions, deduce the equilibrium constant expression. K. Take a moment to write down your answers, and then we will review them. Here are the reactions. Okay, let's go through the solutions. For the first reaction, hydrogen and fluorine forming hydrogen fluoride, the expression is concentration of HF squared, divided by concentration of H2 times concentration of F2. Next, the synthesis of sulfur trioxide. The expression is concentration of SO3 squared, divided by concentration of O2 times concentration of SO2 squared. For the decomposition of phosphorus pentafluoride, it's concentration of P4 times concentration of F2 to the power of 10, all divided by concentration of PF5 to the power of 4. Finally, the reaction between nitrogen and oxygen to form nitric oxide. The expression is concentration of NO squared divided by concentration of N2 times concentration of O2. If you wrote all of those correctly, you have a solid understanding of how to deduce the equilibrium constant expression. This is a fundamental skill. Now, let's explore how the value of K changes when we alter the chemical equation it represents. There are three main ways a reaction equation can be modified, and each one affects K in a predictable way. First, if you reverse a reaction, the new equilibrium constant, let's call it K prime, is simply the reciprocal of the original K. So, K prime equals 1 over K. Second, if you multiply all stoichiometric coefficients in a reaction by a factor, say n, the new constant K prime is the original constant K raised to the power of that factorand. For example, if you double a reaction, the new K is K squared. Third, if you add two or more reactions together to get a new overall reaction, the new equilibrium constant, K overall, is the product of the individual K values. K overall equals K1 times K2. Remembering these rules is very helpful in equilibrium calculations. Let's demonstrate this with a specific example from your notes. The same equilibrium system can be represented in two different ways. Let's call the forward reaction equation 1. The equilibrium expression for this reaction, Kc1, is concentration of CO times concentration of Cl2 divided by concentration of CoCl2. Now let's look at a second equation for this system, which is simply the reverse of the first one. The equilibrium expression for this reverse reaction, K2, has the products on top and reactants on the bottom. K2 is concentration of CoCl2 divided by concentration of CO times concentration of Cl2. The question asks for the mathematical relationship between K1 and K2. If we compare the two expressions, you can see that the expression for K2 is exactly the reciprocal, or the inverse, of the expression for K1. Therefore, the relationship is K2 equals 1 divided by K1. This confirms our rule that reversing a reaction results in an equilibrium constant that is the reciprocal of the original one. It's a direct consequence of how the equilibrium law is defined. We have seen how to define and write the equilibrium constant K, but how is K actually measured in a laboratory? Let's use a common example, the esterification of ethanoic acid with ethanol. The process begins by mixing precisely measured quantities of ethanoic acid and ethanol in a sealed flask, along with a catalyst like hydrochloric acid. It's then left at a constant temperature for 48 hours to ensure it reaches equilibrium. Once at equilibrium, a sample of the mixture is taken and diluted. To prevent the equilibrium from shifting during the analysis, it's quickly cooled in an ice bath to slow down the reaction. Next, the sample is titrated with a standard solution of sodium hydroxide. This titration determines the total amount of acid present in the mixture. The initial hydrochloric acid catalyst and the ethanoic acid produced at equilibrium. To find the equilibrium concentration of ethanoic acid alone, you must account for the catalyst. Since the catalyst is consumed, you calculate how much NaOH was needed to neutralize the known amount of HCl catalyst you added at the start. The remaining volume of NaOH in the titration must have reacted with the ethanoic acid. From this, you can calculate the moles of ethanoic acid at equilibrium. Using the initial amounts of reactants and stoichiometry, you can then determine the equilibrium amounts of all other species. Dividing by the total volume gives you the concentrations, allowing you to calculate the value of K. Now let's delve into the relationship between the equilibrium constant and other thermodynamic quantities, a key higher-level topic. We know that for a reaction to be spontaneous, the change in Gibbs free energy, dG, must be negative. The equilibrium constant K also describes spontaneity. A large K indicates a reaction that lies far to the right in favor of products. These two quantities are linked by a powerful thermodynamic equation. dG naught equals negative RT natural log of K. Let's unpack this equation. Vg naught is the standard Gibbs free energy change, measured under standard conditions of 298 Kelvin, 100 kPa pressure, and 1 molar concentrations. R is the ideal gas constant, 8.314 joules per Kelvin mole. T is the absolute temperature in Kelvin, and Ln denotes the natural logarithm. This equation shows that dG naught and K are inversely related. Let's analyze the implications. If a reaction is spontaneous, dG naught is negative. The right side of the equation becomes positive, which can only happen if K is greater than 1. This makes sense. A spontaneous reaction favors products, and a large K means products are favored at equilibrium. If a reaction is non-spontaneous, dg0 is positive. The right side is negative, requiring K to be less than 1. This means the reactants are favored at equilibrium. Finally, at equilibrium itself, dg0 is 0. This requires K to be equal to 1. This is the condition where reactants and products are equally favored. We can also use the cell potential, E0, from electrochemistry to calculate the equilibrium constant K for a redox reaction. This is another key HL link. There is a direct relationship between the cell potential, E0, and the standard Gibbs free energy change, dg0. This equation is dg0 equals negative N Fe0. Let's define the terms. N is the number of electrons transferred in the balanced redox equation. F is the Faraday constant, the charge on 1 mole of electrons, which is approximately 96,485 coulombs. E0 is the standard cell potential, measured in volts. It represents the potential difference produced by the redox reaction under standard conditions. By combining this equation with the previous one, dg0 equals negative RT natural log of K, we can derive a direct relationship between E0 and K. Setting the two expressions for dg0 equal to each other, we get negative NFE0 equals negative RT natural log of K. Rearranging this for K, we find that the equilibrium constant K is equal to E, the base of the natural logarithm, raised to the power of NFE0 divided by RT. This allows us to calculate the equilibrium constant directly from the cell potential. Let's work through an example that combines these concepts: electrochemistry and equilibrium constants. Consider a voltaic cell based on the reaction between copper-like ions and iodide ions. First, we need the standard reduction potentials for the relevant half reactions. The reduction of copper I to copper metal has a standard potential of 0.52 volts, and the reduction of iodine to iodide ions has a standard potential of 0.54 volts. Since the iodine reduction potential is more positive, it will be the cathode. The copper half reaction will reverse and act as the anode. The overall cell reaction is copper I plus iodide forming solid copper and solid iodine. Notice that we doubled the copper half reaction to balance the electrons. The number of electrons transferred, N, is 2. The cell potential, E0, is the potential of the cathode, iodine, minus the potential of the anode, copper, which is 0.2 volts. Now we can calculate K, using the formula K equals E to the power of NFE0 over RT. Let's assume standard temperature, 298 Kelvin. After calculating the exponent, which is approximately 1.565, and taking E to that power, we find the equilibrium constant K is 4.78. This small value of K indicates that at equilibrium, the reactants, Cu plus and I are favored over the products, Q and I2. This example beautifully connects electrochemistry to equilibrium, showing how these branches of chemistry are intertwined. We've covered the definition of dynamic equilibrium and the quantitative tool, the equilibrium law. But what happens when you disturb a system that is already at equilibrium? This question is answered by Le Châtelier's principle, a powerful qualitative tool for predicting shifts in equilibrium. The principle states, if a change of condition is applied to a system in equilibrium, the system will shift in a direction that partially opposes the change. Let's break down the types of changes we can apply and how the equilibrium responds. The first change we'll consider is a change in the concentration of one of the reactants or products. If you add more reactant, the system will oppose this increase by consuming the added reactant. It does this by shifting the equilibrium to the right, favoring the formation of more products. Conversely, if you add more product, the system will consume it by shifting the equilibrium to the left, favoring the formation of more reactants. If you remove product, the system shifts right to replace it. The key is the system always tries to undo what you've done. The second type of change is the effect of pressure, but this only applies to reactions involving gases. If you increase the pressure by decreasing the volume, the system shifts to reduce that pressure. It does this by favoring the side of the equation with the fewer total moles of gas. By producing fewer gas molecules, the pressure decreases. A decrease in pressure has the opposite effect. Importantly, if the number of gas moles is the same on both sides, a change in pressure will have no effect. Let's continue our discussion of Le Châtelier's principle and examine the effect of temperature and catalysts. The third and arguably most important change is the effect of temperature. This is the only change that alters the value of the equilibrium constant K. To predict the shift, you must first know the enthalpy change, dH, for the forward reaction. An increase in temperature will favor the endothermic direction. An endothermic reaction absorbs heat, and by proceeding in this direction, the system partially consumes the added heat, opposing your change. This shifts the equilibrium. A decrease in temperature will favor the exothermic direction. An exothermic reaction releases heat, and by proceeding in this direction, the system replaces some of the lost heat, again opposing your change and shifting the equilibrium. Consider our example reaction between hydrogen and iodine. Let's assume the forward reaction is endothermic. If we increase the temperature, since the forward reaction is endothermic, the system shifts right to absorb the heat. This would increase the value of K. If we decrease the temperature, the system shifts left, and K would decrease. The final change to consider is the addition of a catalyst. A catalyst works by lowering the activation energy for both the forward and backward reactions by the same amount. Therefore, adding a catalyst does not change the position of equilibrium and does not change the value of K. It simply helps the system reach equilibrium faster. Think of it as speeding up both runners on our escalator analogy equally. They still stay in the same place. We have reached the 10-minute mark of this video. We hope this deep dive into equilibrium has been helpful. If you are looking for expert, personalized support for your IB, A-level, or IGCSE studies in chemistry, physics, or mathematics, please contact DAR Tutors. Our experienced tutors can provide the targeted guidance you need to succeed. You can find our website and contact information on the screen. Now let's return to the lecture to finish up with two advanced HL concepts: reaction quotient Q and ice tables. We've established that K is a constant value for a reaction at equilibrium. But what if a reaction is not yet at equilibrium? To address this, we use the reaction quotient, Q. The expression for Q is identical to the expression for K. For the general reaction, Q is the same product over reactant expression. The key difference is that the concentrations we use to calculate Q are the instantaneous concentrations at a specific moment in time, which are not necessarily equilibrium concentrations. So, we calculate Q using a non-equilibrium mixture and then compare its value to the known equilibrium constant K. This comparison tells us the direction the reaction must shift to reach equilibrium. There are three possible outcomes. Let's work through an example. Suppose we have the reaction N2G plus 3H2G equal to 2NH3G. The equilibrium constant K is 4.31 times 10 to the minus 2 at 700 Kelvin. Now imagine a vessel containing these initial non-equilibrium concentrations. The question is, will the forward or reverse reaction be favored to reach equilibrium? First, we calculate the reaction quotient Q using these initial concentrations. Plugging the values into the Q expression, we find that Q is 1.90. Now we compare Q to K. Q is 1.90, which is much larger than K, 0.0431. Since Q is greater than K, the reaction quotient is too large, indicating there are too many products relative to reactants. Therefore, the reaction must shift to the left to reach equilibrium. This means the reverse reaction is favored, consuming ammonia and producing more nitrogen and hydrogen until the Q value equals K. This is how we use Q to predict the direction of a reaction. We've used Q to find out which way a reaction will shift. Now for the ultimate challenge, how to calculate the actual equilibrium concentrations. For this, we use a tool called an ice table, which is short for initial change equilibrium. Let's work through a classic problem. Hydrogen and iodine react in a 1 Claus cubic decimeter vessel at 450 degrees Celsius. The initial amounts of H2 and I2 are both 0.100 moles. The equilibrium constant K is 50.5. Our goal is to find the equilibrium concentrations of all three species. We start by setting up our ice table. We write the balanced equation, and then rows for the initial concentrations, the change in concentrations, and the final equilibrium concentrations. The initial concentrations are the initial moles divided by the volume. Now for the change. Since we started with no products, the forward reaction must occur. Let's say the change in concentration of H2 is X. Because the stoichiometry is 1-to-1 for H2 and I2, the change in I2 must also be X. The change for HI is plus 2X, because its coefficient is 2. The negative signs indicate reactants are consumed, and the positive sign means products are formed. The equilibrium concentrations are the initial plus the change. For H2 and I2, it's 0.100 minus X. For HI, it's 2X. The next step is to plug these equilibrium expressions into the equilibrium constant equation. The K expression is concentration of HI squared over the concentrations of H2 and I2. To solve this, we can simplify. Notice the denominator is a perfect square, so we can write the equation as the ratio of 2x to 0.100 minus x, all squared equals 50.5. Taking the square root of both sides makes it much easier to solve. The square root of 50.5 is 7.106. Now we have a simple linear equation to solve for x. Multiplying both sides by the denominator gives 2x equals 0.7106 minus 7.106. Rearranging to solve for x gives us approximately 0.0780. Finally, we substitute the value of x back into our equilibrium expressions from the ICE table. The equilibrium concentration of H2 and I2 is 0.100 minus 0.0780, which is 0.022 moles per cubic decimeter. The equilibrium concentration of HI is 2 times 0.0780, which is 0.16 moles per cubic decimeter, moles per cubic. And that's how you use an ICE table. It's a systematic way to calculate the equilibrium concentrations for any reversible reaction, a very important skill for the IB exam. Let's work through another ICE table problem. This time, we'll start with a product, and the problem will involve a quadratic equation, which is a common scenario in HL chemistry. Consider the same reaction, but we'll start with 0.800 moles of hydrogen iodide in a 1 cubic decimeter vessel. The equilibrium constant is still 50.5. First, the setup. The initial concentrations are 0.800 mol DM3 for HI and 0 for H2 and I2. Since we start with no reactants, the reverse reaction must occur. HI will decompose. Let's define the change in HI as 2x. Based on the stoichiometry, the change for H2 and I2 will be plex. This gives us equilibrium concentrations of x for H2, x for I2, and 0.800 minus 2x for HI. Substituting these into our K expression, we get 0.800 minus 2x squared divided by x squared equals 50.5. This again results in a perfect square, allowing for simplification by taking the square root. So 0.800 minus 2x all over x equals 7.06. Rearranging this equation gives 0.800 equals 9.106, which solves to x is approximately 0.0878. Plugging this back into our ICE table expressions, we find the equilibrium concentrations of H2 and I2 are both 0.0878 mol DM3. The equilibrium concentration of HI is 0.6244 mol DM3. Notice that despite starting with only HI, and in the previous problem only H2 and I2, the final equilibrium state is the same. The equilibrium composition is independent of the path taken, provided other conditions like temperature are constant. This is a fundamental property of equilibrium. Let's work through one more ICE table problem where the simplification of taking the square root isn't possible, forcing us to solve a quadratic equation. This is a common and important HL skill. Let's use a different reaction. Consider the dissociation of dinitrogen tetroxide, N2O4 dissociating into 2NO2. The equilibrium constant K is 1.05 at 25 degrees Celsius. Let's say we start with an initial concentration of 2.0 molar of N2O4 in a 2.0 cubic decimeter vessel. We want to find the equilibrium concentrations. Our ICE table. The initial concentration of N2O4 is 2.0 moles divided by 2.0 DM3, which is 1.0 mol DM3. For the change, we'll lose x of N2O4 and gain plus 2x of NO2, giving us equilibrium concentrations of 1 minus x for N2O4 and 2x for NO2. Now we write the equilibrium expression and substitute our equilibrium concentrations. This gives K equals 2x squared divided by 1 minus x equals 1.05. This simplifies to 4x squared over 1 minus x equals 1.05. This equation is not a perfect square, so we must expand it into a standard quadratic form. The standard form of a quadratic equation is x2 plus bx plus c equals 0. Comparing this, we see that a equals 4, b equals 1.05, and c equals 1.05. Now we can use the quadratic formula to solve for x. Substituting the values, we get x equals negative 1.05 plus or minus the square root of a number, all divided by 8. This gives us two possible values for x, approximately 0.407 and negative 0.69. In chemistry, a concentration cannot be negative, so we discard the negative solution. Our value for x is 0.407 mol dem3. Plugging this back into our ice table expressions, we find the equilibrium concentration of N2O4 is 0.593 mol dm3, and the equilibrium concentration of NO2 is 0.814 mol dm3. Solving quadratic equations is a necessary skill for HL chemistry, as not all equilibrium problems are simplifiable by taking the square root. Mastering the ice table method is key to success. Let's test your understanding with 5 IB-style practice questions. Pause the video and try to answer them on your own before I reveal the worked solutions. Question 1 asks for the equilibrium expression for the reaction of sulfur dioxide and oxygen. Question 2 gives you K for a reaction and asks for K for the reverse reaction. Question 3 is a Le Châtelier's principle problem. It asks how to favor product formation in an exothermic reaction. Question 4, for HL students, uses the reaction quotient Q to determine the direction of shift. Question 5, also for HL students, is an IC table problem. You are given initial concentrations and K and asked for the equilibrium concentration of HI. Please pause the video here and attempt these questions. When you're ready, continue to the next scene for the full solutions. Welcome back. Let's review the solutions to our practice questions. Don't worry if you didn't get them all right. The important thing is to understand the process. Solution to Q1. The equilibrium expression is concentration of SO3 squared divided by concentration of SO2 squared times concentration of O2. Solution to Q2. Reversing a reaction makes the new K the reciprocal. So K prime is 1 divided by 2.9 times 10 to the minus 11, which equals 3.4 times 10 to the 10. Solution to Q3. We need to shift to the right. Increasing reactant concentrations, N2 or H2, or decreasing product concentration, NH3, will shift right. Increasing the pressure, decreasing volume, will shift to the side with fewer gas moles, 2 versus 4, so it shifts right. Finally, since the forward reaction is exothermic, DH is negative, decreasing the temperature will shift the equilibrium to the right. Solution to Q4, HL. First, calculate Q with the given non-equilibrium concentrations. Q is 3.0 squared over 2.0 times 1.0, which equals 4.5. Comparing Q and K, we see that Q 4.5 is greater than K 4 times. Therefore, the system is not at equilibrium. Since Q is too high, it must decrease, meaning the reaction will shift to the left to consume products and form more reactants. Solution to QHL. The initial concentrations are 0.15 divided by 5.0 dm cubed, which is 0.030 molar for both H2 and I2. Using the ICE table and solving for x, you should find x equals 0.0234 mol dm to the minus 3. The question asks for the concentration of HI. According to our ICE table, the equilibrium concentration of HI is 2x. So 2 times 0.0234 gives us 0.0468 molar. We've now worked through a comprehensive overview of chemical equilibrium for IBHL chemistry. You should be confident in describing dynamic equilibrium, applying the equilibrium law, predicting shifts with Le Châtelier's principle, and solving complex problems using Q and ICE tables. We began by distinguishing reversible from irreversible reactions. We then defined dynamic equilibrium as a state of balance where forward and backward reaction rates are equal, resulting in constant macroscopic properties in a closed system. We introduced the equilibrium law, K, a quantitative expression that relates the concentrations of reactants and products at equilibrium, and explored how it changes when the reaction equation is manipulated. For HL students, we established key thermodynamic connections, linking K to Gibbs free energy and electrochemistry. Next, we covered Le Châtelier's principle, a powerful qualitative tool for predicting how equilibria respond to changes in concentration, pressure, and temperature. And for HL, we demonstrated how to calculate equilibrium concentrations using the reaction quotient Q and ICE tables, including how to solve the resulting quadratic equations. Mastering these concepts is crucial for the IB Chemistry HL syllabus. We encourage you to continue practicing with various problems. Thank you for watching, and we hope this has been a valuable learning experience. For personalized tuition and expert guidance, please remember to contact DAR Tutors.